The video for the MATLAB or the programming portion of homework 4. So this is the second part of the video. So in the first part I went over setting up the problems, and then in this video I was going to show you how I solved these in MATLAB. And just to be clear, you don't have to use MATLAB for this class. You can use Polymath, or some people are using Excel, but as we get into solving these ODEs, I'd highly recommend using Polymath or MATLAB. And if you're not already familiar with MATLAB, I already said this, but I actually recommend using Polymath just because I feel like it's a little more straightforward as far as how you enter your data to set up the problem. But if you are familiar with MATLAB, I personally like MATLAB better, but I don't think you want to spend a lot of time trying to learn MATLAB because that's not what this class is about. And so, but even if you're using Polymath, a lot of the equations the equations that you're putting in are still the same. So I think that you might not get something specifically from this video, but as far as where I went through setting up the problems, you would still use the same equations in Polymath. So anyway, for problem number 1, we're not actually solving differential equations. What we were doing was, and if you remember, we took first we wrote the equation for the mole balance for a batch reactor, and then we wrote a generic rate law where we said that the rate was equal to K multiplied by Ca to alpha. And the reason why we did that is because we don't know the order. So we were given data and we're trying to figure out what the order is and what the rate constant is for our rate law. And so then if we took the natural log of that equation, we ended up with something that resembles a straight line. So y equals mx plus b. So then we know that alpha is equal to the slope and b is equal to the natural log of your rate constant. So once you had this, what you could do was plot the natural log of dc dt versus the natural log of Ca, and then you would do a linear regression and get this equation. So you would get m and b. And so the hard part of this, or not the hardest, but the biggest part of this problem is getting this dCA dt from the data. And so if you remember, there were 3 ways you could do that. You could do graphical differentiation, you could use numerical differentiation formulas, or you could get a polynomial through regression and then differentiate that. And so I actually wrote a program that does all 3 of these just because I wanted to compare what I got with the different methods. And the reason why I did that was because when I first went to solve this problem, I started out with number 3, so differentiating a polynomial. And I didn't feel like I was getting a very good answer because no matter what order I picked, it always said that it was a bad fit. And so I went ahead and solved it using these other 2 methods as well. But I think that, like, usually with these problems, I try and do the polynomial first because that's usually the fastest, at least what I think is the fastest. But if you can't get a good fit, then, if you were actually doing lab experiments, you might need to go back and get some more data points, or use one of these different methods. So all you do for this problem is put in your data. So we had time and we had Ca, and then so right away I just took the natural log of Ca because I know that I'm going to need that. You can get for the polynomial method, which is what I have first, you can get your polynomial a few different ways. First of all, you can go through these MATLAB commands, which I'll show you in a minute. Or you can plot this, and I want to show you real quick why this ended up not working very well to plot it and do it on the plot, just so you can see why I ended up doing it like this. So I'll just make sure real quick that nothing else is plotting. Okay, and then I'm going to run this. Alright, so this is the data, and so if you go in here and go to Tools, and then Basic Fitting, then you can try and fit your data. And first of all, you want to show the equation, get some significant digits, and then I tried right away maybe doing a fifth, and you can see it says polynomials badly conditioned, and I mean you can kind of see that. And so then maybe try a different one, and it doesn't, for some reason it doesn't pop up again with the polynomial badly conditioned, even though I know this one is too. And so the kind of the issue I ran into with this is if doing it this way, so then you get this polynomial, so this is D, so this would be CA is equal to this, and the x's are t's. And then you can take the derivative of this, so you have dCA dt. And so if you do this by hand, like if you write this down and then do it by hand, you'll notice that this is to the -16th, to the -13th, -9th. And I think that because I wasn't getting a good answer putting this directly in, and I think it's because I was losing too many significant figures, whereas if I run it through the code, that wasn't happening. So I just wanted to show that, because for some reason I couldn't get this to work at first, but then when I went and did it like this, instead of entering this directly in, for some reason it worked, even though I don't think the answer is that great. So if you're doing it the polynomial method and you can't get it to work by typing in whatever polynomial you get, you might want to try putting in these commands. So I'll show you what these are. So first of all, this polyfit is fitting the data, and I'm saying that I want a 5th degree polynomial, and this is what I mean. Like, I went through and, like, you can even see down here, because I ran it a minute ago, and it's saying that the polynomial is badly conditioned, add points with distinct x values, or reduce the degree of the polynomial. And no matter what I picked for the degree, it always had that warning. So I just don't know if this method was working very well. And so then the polyval, so this calculates this. So I have a polynomial, and this is calculating what it is at each point t. So, like, I'll just show you that real quick. So if I check that, it'll show up. So this is what it's calculating for CA from that polynomial. And I did that mainly so I could plot the TCA and the TCA calculated, just to kind of see what they look like. And I'll just try running that real quick. I can't remember exactly how it looked. So yeah, this is a polynomial calculated, and I mean, you can see it's not a very good fit, but like I said, no matter what I picked for the order, it wasn't a good fit. So I'm gonna mark this out again. So then I took the derivative of it. So this polyder is, so you can take the derivative of a polynomial. So then I ran this command again, where I calculated the value of the polynomial at each time t, because that's what I need to plot. And so remember, I'm finding the dCA dt, but I need to calculate that at each point. And So then I take the natural log of it, so that's what I'm doing here. I'm doing this polyfit again, so now I want to fit this, so I have this, so I have the natural log of CA and the natural log of CA dt using the polynomial method, and I'm fitting this with linear regression. And so then this should be, this polyfit, or fit poly, should be what, I'll just comment out these others real quick, or block them. So this should be, this equation that it gives you. So then if I run this again, so you can see it's telling me it's badly conditioned, which I already know. But then I get, so this is M and this is B. So I got 2.1876x minus 4.7137. And so then I know that M, or alpha, is 2.19, and the natural log of Ka is this. So then you could calculate Ka from this. But I did the other methods as well because, like I said, this just isn't, I don't think this is a great answer. But that's how you do it. So I just wanted to show you that so you know how to do it. And I think that probably the most popular method for solving these, or getting that, would be either polynomial or graphical, but you can use this finite difference method too. Alright, so the formulas are on page 263, and it's just finite difference method. And you don't need to worry about how these formulas were derived if you don't already know. But it's basically just plug and chug. And so I just wrote a loop to go through. So so the formulas are different for the first one and the last one, and then the middle calculations are all the same. So I did the first calculation, so I have dCA dt using finite difference, and this is the first point in my array, and then I calculate that, and using, so this is referencing the first point in CA, second point in CA, third point in CA, and then same thing with time. And then this is the middle values, and so I'm going from 2 to t minus 1, or the length of t minus 1. And so I have, and if you look at the formula, you'll see that CA, and then this is going to always be the point that you're looking at plus 1, and this is always going to be the point that you're looking at minus 1, so that's how I got that. And then the reason why I put in the t's like this, normally you can just, so the other thing with finite difference method is you normally want evenly spaced data, and so normally you could just calculate what delta t is and put that in for everything, but this data actually changes, so for about half of it it's spaced by 10, and for about half of it it's spaced by 100. And so that's why I put this in like that. And that's also why I recalculated delta t down here. And so then I have, this is the very last point, and so these formulas are literally straight out of the book, and so if you go look at those, I think it'll be pretty apparent how I got those. And then I need to take the natural log of that. So this calculates dCA dt. Take the natural log, and then I did the same thing. I just used this. So I could either plot this, like I'll just show you real quick. So if I run this and plot that, and I think that it's, this obviously isn't that great of a straight line, and I think it's because the data isn't evenly spaced, but I'm just going to go ahead and fit that anyway. And I can also see, well, actually I don't have it unchecked anymore, so I'll just look at that in a minute. But you want to do linear, and then you can go to show equation. And so then this is what it gives you. So for this y equals mx plus b, so you would have 3.6 for alpha and minus 4.7 for the natural log of Ka. And so you can get that from here, or you don't actually need to plot it. You can just, like if I comment that out again, and then take that semicolon off and run it, then see it gave me the same thing here, because this is fitting it, and then I'm saying fit the data, ln of Ca, ln dCa dt, and the 1 is for linear regression. So that's what I get. And so then using the graphical method, you can, and this isn't exactly the graphical method, but it's what you can do in MATLAB. So you can use this diff command. And so what diff does is it goes down this array and it says, okay, C2 minus C1, and then the next, and it stores that in a spot, and then the next spot would be C3 minus C2. And so actually, I mean, I'm sure you already know this, but I'll just look that up real quick. So diff MATLAB. So there's actually a lot of really good resources online for MATLAB if you're trying to learn how to use this. So this is what the diff command does. So it goes down the array and it says, okay, x2 minus x1. So in our case, this would be Ca, like if I go back to this, that would be, so if you remember with the graphical method, when we did this by hand, we just went down and calculated each one of these individually and divided it. So, but this will automatically do it for you. So diff Ca, which would be x2 minus x1, the next spot would be x3 minus x2, and then down, and then the same thing with t. And then you need to do the dot divide with this, so it knows to divide each element. And then once you have that, you take the natural log of it. So it's the same thing. You're calculating dCa dt, and then you need to take the natural log. And then so what you get with this will actually be one element shorter than Ca was, and so I just removed the last element from Ca, and then you can plot it and do the graphical linear regression, which I'll just plot that real quick so you can see it. So out of all the methods, this one seemed to come up with the smoothest graph, but I'm just not sure how, like if any of these are that perfect. So yeah, this is what you get with this one. So tools, basic fitting, and then I just chose linear, and then show equation, and then you can get some more significant figures. And so this is what you get for that, and then, but you don't have to plot it. You can just do what I did here, where I have the polyfit, and so this polyfit does the same thing I just did on the graph. So I'm saying fit the data ln of Ca to ln dCa dt graph, and then 1 for linear regression. So then if I run that, no, actually I'm going to, okay, so then if I run this, so then I have all three of them here. So I mean, so you can see it's still showing the polynomials badly conditioned, which I already know. And then this is what I got for the three equations using the three methods. So then, so for the assignment, whichever method you used, you would get one of these. And since it didn't specify which method you had to use on the assignment, I think any of these would be okay. But in real life, you would want to try and differentiate what's good and what isn't with the different methods. So for problem 2, if you remember from the first video for homework 4, or for part 1, we derived this equation, the ln of Ca naught over Ca divided by Ca naught minus Ca equals K1T Ca naught minus Ca minus K2. And then, if you remember, this also looks like a line, so you have y equals mx plus b. And this method specifically said to use the integral method, which, if you remember, you basically solve the problem. Well, you guess the order of your rate if you don't know it. I don't actually think I would want to use this method if I didn't know what the rate was. In this case, we were given the rate law, and so we were able to just put the rate law into the equation for the batch reactor and integrate it, and then we were able to get this. And so the way you know if your rate was correct is when you plot this, it should be a straight line, and if it's not, then you know that the rate order that you guessed was wrong, and so then you have to try another one. So that's why I'm not sure if I would use this method if I didn't know what the rate order was, or the order of the rate. And so with this one, we wanted to plot the natural log of Ca naught over Ca divided by Ca naught minus Ca, so this, versus T over Ca naught minus Ca. And then we know that, then we get back an equation, so we plot these two things, do a linear regression, and we get back an equation that is y equals mx plus b. So then we know that m will be equal to k1 and b will be equal to negative k2. And then we can calculate what the k and m were or capital M and k in the rate law that was given, because we had already said that k1 is equal to this and k2 is equal to this. So if I pull up number 2, so this was actually really simple, because, I mean, you could have probably done this in Excel or some other program pretty easily, but anyway, so you put in your data, so we had Ca is equal to this, T is equal to this, and then, so I know that a lot of people ended up using 0 for Ca naught, but I actually went in and fit the data, and I used a second degree polynomial for that. And then I calculated so this polyval, so I calculated, I calculated the values of Ca at each point t, and I did this just to see how the fit looked, and I'll just plot that real quick. Alright, so yeah, this was so these blue circles are the actual data points, and then this line is what I calculated from this polyfit. So I think it looks pretty good, and plus it didn't tell me that it was poorly conditioned or anything like that. So then I can calculate what Ca naught is at 0. So that's what this polyval just calculates, so that the Ca poly is your polynomial, and whatever you put here is what it calculates out. So like in this case, it calculated at point t, and in this case I'm calculating at point 0 to get Ca naught. And I don't think this was required, I just did it because it seemed better to me than just sticking in 0 for Ca naught. And okay, so then I wanted to, so this is y in this scheme, and this is x. So really I just calculated these. So I have y is equal to the natural log of Ca naught dot divide Ca dot divide Ca naught minus Ca. And then x is equal to t dot divide Ca naught minus Ca. And then I just fit it. So so I'll plot that now. Comment this one out. So it's mostly a straight line. So once again, you can do tools, basic fitting, linear, show equation, and then, so that's what you get. So m 0.88 and b minus 3.7. So if I go, and then if I go back into here, I also fit it here, so I have the fit is equal to this command polyfit. So I'm saying to do regression on x and y for order 1. So basically linear regression. And so then if I run that, then this is what I get, and it's the same thing. So you can do it either way. So then you would just take this, and I mean, I could even write more code to calculate this stuff from this, but now we know that this m is equal to k1 and b minus k2, or b is equal to, well, b is equal to minus k2, so k2 is equal to 3.67, and then you can calculate m and k. All right, so for number 3, let's find that real quick. I'm not going to spend very much time talking about it because it was basically identical to number 1. I used the exact same code. The only thing I changed was the t, because obviously we had different data, and ca. So I just put different data in, and everything else is exactly the same. So then if I run this, this is what I ended up getting for the different fits. So for polynomial fit, so this one actually looked a lot closer for each one than the first one did. So it looks like it was about, alpha was about 1, and k, well, I didn't calculate k, but you know that this is the natural log of k, so you should be able to calculate k. I actually made a MATLAB video a while back where I went through this setup in great detail of how to calculate, of how to solve 2 or more ODEs in MATLAB. And so I went through example 4-6 and in pretty great detail, like I think it was a pretty long video, and I showed basically how all this was set up as far as the writing this function. And so for this problem, I'm pretty much using the same code. The only thing I changed was these constants and RA prime. All right, so these were the equations from problem 5, and if you, so these are the equations you should have ended up with that we need to solve. This dx dw equals minus RA prime over FA naught, and dy dw is equal to this. So this is the pressure drop, and this was your mole balance. And then you had an equation for the rate, for the concentration, this is your stoichiometry, and then you just have all these constants. So just to go through this real quick, the first thing you would need to do is write a function that calculates the right-hand side of your equation. So that's this, so it should calculate this side. And so I did that. I have, and yeah, so the other thing is, since this is a function, I need to make sure it's called the name. So whatever you call your function right here, your file needs to be named the same, otherwise it's not going to work. And so then I have dy dw is equal to this, and so that's 2 rows, 1 column of zeros. And so I have the constants. So I have epsilon, which we calculated that. Yeah, that's minus 0.5. K prime is 0.5, CA naught is 0.2, V naught is 0.15. We know that FA naught is equal to CA naught multiplied by V naught. Alpha is equal to 1. And then I put in the equation for RA prime. So that was equal to KCA squared. And then I had, let's see, well, I have this for the concentration. So CA naught, 1 minus, and then if you remember the way I have to reference this, I can't, the way MATLAB works is I can't have an X and a Y, which is technically what I'd want. I can only have one dependent variable. And so that's why I have this set up with the two, well, okay, so that's why I have that set up with the 2 and the 1, and then I just defined y1 is equal to x, and y2 is equal to y. So dy dw, this is technically what it is. And so then the way I'm referencing this, so the y1 is x, so this would be 1 minus x divided by 1 plus epsilon x squared multiplied by y2, and so this is the pressure drop y squared. And then the same thing down here, so the dy dw, and I have minus alpha is equal to 2, and then that's y multiplied by 1 plus epsilon x. And so you can see why in the last program, when I had the dy dw, I put in this equation, the RA prime F divided by FA naught, instead of, because you could take the CA over here, put that in there, and then put your rate directly into there, and then put in this whole equation for this. But if you do it like this, then you can reuse this code, because all you need to do is change what your rate is, because this equation will never change, the RA prime over FA naught. So this is how you calculate the right-hand side. So then what you need to do is write a script that uses ODE 45, or you could probably use ODE 21, and so this is the solver that solves the differential equations. So I think this is a Runge-Kutta solver. And so what you're doing is it's getting the right-hand side from this function, and this is your initial value for W. So W is 0, W naught is 0, and W final is 1. And then these are your initial values for X and Y. So X naught is 0, and Y naught is 1, because when there's at the beginning there hasn't been a pressure drop yet, so Y over Y naught is equal to 1. And so this will solve these equations. So then I'm plotting, this is X, so the Y semicolon 1, that's X, and Y semicolon 2, that's Y. So this is your pressure drop. And I'll just print those out real quick so you can see what we're getting. So I'll just do W and Y. So then if I go over here, so you can see these are the values it's using for W. So just between 0 and 1. And then Y, so this says X. And this is Y. So you can see the initial values of 0 and 1. And so this is why you need to call this like that. So this is saying every row in the first column, and this is saying every row in the second column. So anyway, that's how that's done, and I'll just run this again. So this is the plot I got, and so this is Y, the pressure drop, and this was X, the conversion. And these are kind of small. If I was actually going to use this plot, I would go in and edit these, but this is the weight, and then X and Y. So, like I said, I kind of went through this a lot faster, but I already did a really detailed video on this code. So, if you're kind of confused about this, then either play around with it, I mean that's the best way to figure it out, or go back and watch that other video. For number 6, I actually forgot to write down the summary of equations, so I'm just going to go through this. So you solve this exactly the same way as the last problem. So you're going to use ODE 45, or you could use ODE 21, I think. And you're setting this up exactly the same way. So first of all, you need to write a function, and I just called this function semi-batch, so then just make sure it's named the same, semi-batch.m. But this time, I'm solving 5 ODEs instead of just the 2. So this time I have dc dt is equal to zeros, and then I have this 5, 1, and I'll just run this real quick so you can see what that's actually doing. So it's basically just a column of zeros. And so then I just defined what each one was. So the first one is, since I can't, and I just used y again, but I can't have like CA, CB, CC, CD, and CE. I have to have something like y1, y2, or x, or whatever variable I decide to use. It has to be the same for all of them. So then I have, so CA is the first one, CB is the second one, CC is the second one, or third one, CD is the fourth one, and CE is the fifth one. And then this is wrong because this should be 3, 4, 5. So this is referencing the spot in this array. So first one CA, CB, CC, CD, and CE. And then all I do is the same thing. I put in all of my variables, and then these are the differential equations I'm solving. So for the variables, I believe CB0 was given. It was 1.6. FB0 was 0.12. We know that V0 is equal to FB0 over CB0. K was, well, okay, so I have 5 over 60 because K was given per hour. I needed that per minute. And then I put in my rate loss for each one, so I know that RA is equal to minus K C1 C2. And I can't remember if that was given. I think I just assumed a elementary rate law. And then using stoichiometry, I know that RB is equal to RA, RC is equal to minus RA, RD is equal to minus RA, and I don't know why I have 2 of these. RE is equal to minus RA. And then the initial volume given was 1450, and then we know that V, like the volume, is equal to the initial volume plus V0 times T. So you need to put that in. And then these are the differential equations you're solving. And so you have dCT, dCA dt, and I just have dC dt because I can't have dCA dt. So this is referencing the different locations. So 1, 2, 3, 4, 5, and so I know that the first one is which is dCA dt is equal to RA minus V naught over V times CA, which is C1. I know that, so the second one, dCB dt is equal to RB plus V naught over V multiplied by CB naught minus CB. dCC dt is equal to RC minus V naught over V multiplied by C3. dCD dt is equal to RD minus V naught over V multiplied by C4. And dCE dt is equal to RE minus V naught over V multiplied by C5. So once you have this set up, then it's the same thing. You just write a script that calls ODE 45. So this is saying T and C are equal to, and so then I give it this function so it can calculate the right-hand side. And then this is the initial and final value for T, so 0 to 50 minutes. And I can't remember if the 50 was given or if I just played around with it, but that's what I used. And so then the initial values, so for C1, so this is CA naught is equal to 0.8, CB naught is 1.6, and then the rest are 0 because they haven't been produced yet. So anyway, then I'm just plotting this, so I'm plotting each concentration, and I just plotted, so C, D, and E should all be the same, and so I only plotted C. I only plotted one of them. I plotted CA, CB, and CC, and so I'll just show you real quick what you end up getting from this. So if I run this, then first of all I have the time, so 0 to 50. Now these are the concentrations, so this would be CA, CB, CC, CD, and CE. And you could read your final value off this if you needed to. And so then this is what the plot looks like. So if I go to the legend, let's see, insert. So this is, so this is CA. This one is CB. And this is CC, CE, or CC, CD, and CE. And I'll upload these MATLAB files to the class webpage so you can, or to Canvas so you can look at them.